Hi, let's get jumping. We're going to talk about projectiles that are launched at an angle other than 0. So these are going to be going up in the air and coming back down. So we have a projectile motion with a general launch angle, something other than horizontal. And it's a little bit more complicated because now we have a vertical initial velocity in addition to our horizontal initial velocity. And we must begin problems like this by resolving our velocities into their components. Again, taking a vector apart is called resolving it. And we need our vertical component and our horizontal component. So just a review I imagine for you on finding the components. If we have a velocity vector, v0, that makes an angle with a horizontal of theta, the initial velocity in the y direction can be found by resolving the component v0 sine theta. And similarly for the initial x component, we resolve it by v0 cosine theta. v0 is the magnitude of the initial velocity vector. Then we proceed to work these problems just like we did with zero launch angle problems. We list the information we know in the x direction, list the information we know in the y direction. Then we find the equations for the motion that we're interested in. And at the end, we put everything back together, compose vectors if we need to, and make sure that we answered the question that we were being asked. Here's your multiple choice. Now I have a sample problem for you, and after the sample problem I'm going to go through some of the properties of projectile motion, some of the things that may help you solve some more complicated problems, ways of thinking about the motion. This problem, however, is very straightforward, so let's go ahead and take a crack at it. Okay, we have a soccer ball kicked with a speed of 9.5 meters per second at an angle of 25 degrees above the horizontal. If the ball lands at the same level from which it was kicked, how long was it in the air? Well, I start out by drawing a picture. Can you believe that? I'm going to draw a picture. So that's the path that I think the soccer ball is going to take. I'm going to draw the ground that it's flying over and the initial velocity vector is 9.5 meters per second. That's the initial velocity, and at an angle of 25 degrees. 25 degrees. And I want to know how long it was in there. So that's a time. Start out by writing my information down for the x direction. x0 equals, well, I'm going to say it starts at 0. X, how far it goes down range, we don't know. We don't really care. How fast is it going in the horizontal direction when it starts? Well, we want the x component of the velocity, of the initial velocity, so that would be 9.5 cosine of 25 degrees meters per second. And the final velocity in the x direction is equal to the initial velocity in the x direction. There's nothing to accelerate it in the x direction. So we're going to note that as acceleration in x direction is 0 meters per second squared. And the time, we're looking for the time. Don't have enough information in the x direction to find the time, so we'll have to look at the y direction. Well, the ball is starting from the ground, so I'll say that's 0 meters. Where's the ball ending up? Oh, it's ending up on the ground. So it ends at 0 meters. That doesn't mean it didn't go anywhere. Just means that it returned to its starting height. The initial velocity in the y direction is equal to 9.5 meters per second times the sine, because we're looking at the opposite side of the triangle, sine of 25 degrees. Do we know what the final velocity is? Yeah, what goes up comes back down, but in the opposite direction. So we're landing at the same height that we took off from, so the final velocity in the y direction is equal to our initial, but in the opposite direction. So it's going to be a negative 9.5 sine 25 degrees meters per second. And there is an acceleration in the y direction. Obviously our velocity has changed from going up to going down. And it's the acceleration due to gravity, so it's a negative 9.8 meters per second squared. And the time is what we're looking for. Well, we have a lot of information in the y direction, all the information that we need to find the time. And since time is the only thing that we don't know, let's pick the simplest equation that we have for velocity and time, and that would be v is equal to v0 plus at, and I'm going to note the y directions. There we go. And we're solving for time. So the time is equal to Vy minus V0 in the y direction over acceleration in the y direction. So Vy would be negative 9.5 sine 25 minus V0 y, which is 9.5 sine 25 over the acceleration, which is negative 9.8 meters per second squared. Oh, that doesn't add up to 0 because they're both negatives. If it's a negative minus something, it comes out to be a negative number. Oh, that's good. I was worried there for a second. So the time is 0.82 seconds. Not too bad. Again, there's a lot of work to this because we have motion in 2 dimensions. Next up. So we're going to be talking about projectiles launched over level ground for the time being. They're highly symmetric, and it's really handy if you know these characteristics because the symmetry will help you solve these problems. If you forget all about symmetry, you're going to have a hard time. So, trajectory. Now, we are going to use the term trajectory a lot. It's the path that's traveled by any projectile plotted on a XY graph. We have the Y direction and the X direction. We're not going to be plotting against time in our trajectory. So, this is a parabola. It has the same equation as the parabolas that you use in math class. So you can visualize this. You can see that the symmetry is apparent. The left side of the trajectory is a mirror of the right side. The range is how far the projectile travels horizontally. The maximum height, guess what, is how high it goes. Okay, and at the top, when it reaches its maximum height, remember that it stops moving in the vertical direction for an instant. Notice, in the vertical direction, the horizontal motion remains constant. So only the y component of the velocity goes to 0 at the tippy top. Okay, I think I just said that. So, for a projectile that's launched over level ground, the maximum height occurs at the halfway point. It's a point of symmetry. The halfway point is a point of symmetry. It's our highest point. It's half of our time. The acceleration is always down at g, at 9.8 meters per second squared, for the entire trajectory. It doesn't ever change. Gravity never turns off. The velocity. The velocity is tangent to the path. It points in the same direction that the ball is moving. The components of the velocity. If you were to resolve the components all along the path, you would see that the x component is a constant and the y component changes due to the effects of gravity. So notice how the vertical velocity changes. On the way up, it goes slower until it's not going up anymore. And then it starts to go down, and it's going faster on the way down. The maximum speed is at the beginning and at the end, if it's launched over level ground. The launch angle is symmetric over level ground. The angle that the velocity makes with the horizontal is the same at the beginning and as at the end. The only difference is at the end it's negative. The time of flight for a projectile can be calculated from its halfway point. Again, we're making the assumption that the projectile is traveling over level ground. If it isn't, we don't have this type of symmetry. So the projectile spends half its time traveling up and half its time traveling down. And here's your free response question. This is very similar to the soccer ball question earlier. Give it your best shot, and we'll see you in class.